The number e is one of the most fascinating and important constants in all of mathematics. There are several ways to define the number e. We shall take the approach of infinite series. So definition we define Euler's constant e to be summation 1 by n factorial n running from 0 to infinity. Other words, it's this familiar 1 plus 1 by 1 factorial plus 1 by 2 factorial plus so on. Before we even begin any analysis of this number e, we must first of all show that this infinite series converges. That's rather easy because once you have written it as 1 plus 1 by 1 factorial plus 1 by 2 factorial, you can just write it as less than or equal to 1 plus 1 by 1 plus 1 by 2 squared plus 1 by 2 power 3 plus dot dot dot. Right? The right hand side is a geometric series that certainly converges. The RHS is a geometric series that converges. So LHS converges as well by the comparison test. So we got a very simple proof that this series summation n equals 0 to infinity 1 by n factorial indeed converges. And we are just calling what it converges to be the number e. Now this number e has a number of special features that we shall explore once we define the exponential functions and relate it to this constant e. We shall do that after we develop some amount of calculus. But let me just state and prove one really interesting fact about this number e. It's the fact that this number e is irrational. We have already seen that square root of 2 is irrational, and the proof was not that hard, though elegant. Here we have a very elegant proof, but somewhat little bit more involved. Theorem e is irrational. Let's see a proof. So what we do is the following. We know that e is just 1 plus 1 plus half plus 1 by 3 factorial 1 by 2 factorial plus 1 by 3 factorial plus so on, right? Now what we do is the following. We are going to fix n and take the first n terms to the left. That means we are going to consider e minus 1 minus 1 minus 1 by 2 factorial minus 1 by 3 factorial dot 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 minus 1 by n factorial. Okay, we are considering the first n terms in the expansion of e and subtracting it from e. Now this is certainly going to be equal to 1 by n plus 1 factorial plus 1 by n plus 2 factorial plus dot dot dot. It's going to be this infinite series. Okay, so clearly this quantity star, which is e minus this, is certainly positive. Star is certainly positive. Okay, now assume e equal to p by q, p comma q coming from the natural numbers. I'm going to get a contradiction. I'm going to assume that e is rational and somehow arrive at a contradiction. Okay, now choose, we had fixed this n, right? Now choose n to be greater than q. Okay, the same manipulation obviously holds. I'm just I had fixed n, I'm just choosing that fixed n to be a quantity that is greater than q. Of course I can do that. Okay, now what I do is I multiply star by n factorial. Okay, so I get n factorial into e, which is just p by q in our new notation, p by q minus 1 minus 1 minus 1 by 2 factorial dot minus 1 by n factorial. Okay, now since our assumption is that n is greater than q, n factorial divided by q will be a natural number, right? Indeed, when I expand this out, every single term will be a natural number. So this is a natural number, Okay, in fact a natural number which will be positive. Of course, natural number itself includes positive, so I needn't have said that. Okay, it's going to be a natural number. But this expression e minus 1 minus 1 minus 1 by 2 factorial was actually equal to, 1 by n plus 1 factorial plus 1 by n plus 2 factorial plus so on, right? So let's multiply this by n factorial. Whatever this natural number is, it's got to be equal to, this natural number has got to be equal to n factorial divided by n plus 1 factorial plus n factorial divided by n plus 2 factorial plus so on, right? This is just because this original expression was equal to this 1 by n plus 1 factorial plus 1 by n plus 2 factorial and so on. Okay, now this leads to a problem. This is actually equal to 1 by n plus 1 plus 1 by n plus 1 into n plus 2 plus so on, right? Which is certainly going to be less than or equal to, in fact strictly less than, I can be more precise, less than 1 by n plus 1 by 1 by n plus 1 squared plus so on, which is a geometric series, so we have to compute the sum. This is in fact equal to 1 by n plus 1 divided by 1 minus 1 by n plus 1, right? This is just 1 by n plus 1 minus 1 by n plus 1, which is equal to 1 by n, right? This 1 by n is certainly not a positive number, positive integer, right? This is a contradiction. Hence E is irrational. So just some little bit of manipulation with infinite series immediately gave us the fact that the number E is not going to be a rational number. Okay, this was a nice proof. Now let's relate E to another limit that you are familiar with. You are probably familiar with, I must add. It is known that E can also be defined as limit n going to infinity 1 plus 1 by n the whole power n. Okay, so E is also equal to this limit. Why is that? Why is the series that we have defined also equal to this limit? Well, this is nothing but summation limit n going to infinity summation k running from 0 to n choose k. This is n choose k. Okay, this is n factorial by k factorial into n minus k factorial. N choose k 1 by n power k. Okay, this is just binomial expansion. I'm just using the familiar binomial expansion. I'm writing out what 1 plus 1 by n the whole power n is. Okay, now this is interesting. We got some summation, but it doesn't look very similar to what we have. but given that there is n choose k which involves factorials, there is some hope. Okay, so let's expand this inner part further. So this is summation k equals 0 to n factorial by n minus k factorial times k factorial into 1 by n power k. Okay, so which is just summation k equals 0 to n into n minus 1 into dot 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 n minus k n minus 1. Okay, that's essentially n minus k plus 1. So I'm just essentially cancelling out the k factorial from both the numerator and denominator. So this divided by n minus k factorial into, or rather what I shall do is I am cancelling n minus k factorial. Sorry, I made a mistake. When I cancelled out n minus k factorial, all the terms from 1 to dot 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 n minus k will get cancelled in the numerator. So I'll be left with k factorial. Okay, small correction. K factorial into n power k. Okay. Now observe that there are k terms here. N minus 1, n minus k minus 1 all the way. And in the denominator we have n power k. Okay, we have n power k. So it's easy to see, that n into n minus 1 dot 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 n minus k minus 1 by n power k as limit n going to infinity, this is just going to be equal to 1. Okay, this is going to be equal to 1. I leave it to you to check this. This is fairly easy exercise. Okay, so what we have is we have summation k equal to 0 to n, some quantity divided by k factorial, and that quantity goes to 1 as n goes to infinity. Well, imagine you have this expression limit n going to infinity summation k equal to 0 to n. What if I could pull this trick? What if I could write this as k equals 0 to infinity limit n going to infinity of n into n minus 1 dot 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 n minus k minus 1 by n power k times k factorial. We know that this limit is got to be equal to k factorial. We will end up with summation k equals 0 to infinity 1 by k factorial, which is e. Which is exactly e. The only problem is this step where I'm just sneakily taking the limit inside and applying the limit requires a proof. It's not always true that you can just interchange stuff like this. Please recall one of the examples given in the very first week of lectures where I showed that carelessly interchanging summations can lead to nonsensical results. So we need to justify why this interchange of limit and summation is a valid operation. In fact, whole of analysis is to make sure that such operations are valid and to provide the reasoning why they are valid and the hypothesis under which they are valid. So this justification is provided by a theorem called Tannery's theorem. The theorem runs as follows. If S of n equal to summation k greater than or equal to 0, fk of n, okay, is a finite or convergent sum for each fixed natural number or fixed n greater than or equal to 0. So what we have is, for each n I'm given a series expression. Okay, this is either a finite or a convergent sum. I don't really care which it is. So for each n, I am given a sum that runs over k. This sum could be finite, this sum could be convergent. It really doesn't matter. Suppose number 1, limit n going to infinity of fk of n is equal to n. Is equal to fk. Just fk. Number 2, for each fixed k greater than or equal to 0, we have mk in our plus such that modulus of fk of n is less than mk for all n in the natural numbers, and summation mk as you run through k is less than infinity. Okay, then the conclusion is limit n going to infinity of summation k greater than or equal to 0 fk of n is in fact equal to summation k running from 0 to infinity of fk. Essentially, we have taken the limit inside. To understand what Tannery's theorem is trying to say, it might be a good idea to draw a grid. So we have this S1, which is supposed to be summation f kn as k goes from 0 to infinity. Okay, so essentially let's expand this sum out. So S1 will nothing but f01 plus f11 plus f21 plus dot dot dot. Similarly, S2 would be just f02 plus f22 plus f23 plus dot dot dot. Okay, and similarly you have S3, S4 and so on. You have these infinite sums. Okay, now what we are trying to do is we are trying to determine the limit as you go down. Okay, that's what limit n going to infinity of summation k greater than or equal to 0 fk of n is supposed to be. This is just s of n, right? This sum is just s of n. We are trying to find the limit as you go down the grid. Okay, we are also given that if you go down each one of these grids, each one of these columns in this grid, you have a limit. Okay, we are calling this limit f0, we are calling this limit f1, we are calling this limit f2 and so on. What Tannery's theorem says is that under this specific condition 2, which just says that for each fixed k, we have a bound on fk of n's mk such that summation k greater than or equal to 0 mk actually converges, then to determine this limit of the essence, it's enough to just sum up these. Okay, so essentially we are giving a condition under which you can interchange the limit and the summation. Let's see a proof. Proof. First of all, it is clear that summation fk greater than or equal to 0 fk converges. In fact, absolutely. Why is this the case? Well, look at hypothesis 2. What it is saying is that for each fixed k, fk of n is actually bounded in absolute value by mk, and summation k greater than or equal to 0, mk is less than infinity. Okay, in particular, this fk, which is nothing but limit n going to infinity of fk of n, must also be bounded in absolute value by capital Mk. And since summation k greater than or equal to 0 Mk is convergent, by comparison test, summation Fk will also be convergent. So I'm going to leave these minor checkings to you. So first of all, we have that summation k greater than or equal to 0, Fk converges. Now the term we are interested in is Sn minus summation k greater than or equal to 0, Fk. Okay, what we want to show is that this, which is actually a number, even though I've written it as a series, what it stands for is actually the term that it converges to. We want to show that given any epsilon, so fix epsilon greater than 0, we have to find an n such that modulus of Sn minus this summation k greater than or equal to 0 Fk is less than epsilon. Okay, so to do this, first choose n of epsilon such that summation k greater than n of epsilon of Mk is less than epsilon by 3. This can certainly be done because these summation Mk's converge. So you can make the tail as small as you want. Okay. Now what you do is for each k choose nk of epsilon such that modulus of Fk of n minus Fk is less than epsilon by 3 n of epsilon. Now you might be wondering why I am pulling constants out of the air. You will understand in a moment. Why I am pulling out these. I'm putting epsilon by 3 n epsilon. So what we have is that each Fkn converges to Fk. So for each k we can find some nk of epsilon such that mod Fkn minus Fk is less than epsilon by 3 n epsilon. Okay. Now what we do is set capital N to be just maximum of n1 epsilon, n2 epsilon, n epsilon of epsilon. Okay. Recall this n epsilon was the point at which the tail of the series summation Mk can be made less than epsilon by 3. For each k we can choose an nk epsilon such that Fk and n and Fk are at max epsilon by 3 n epsilon close. Now you are choosing another n to be the maximum of the quantities n epsilon, n2 epsilon, n epsilon epsilon. Okay. Now what does all this complicated jugglery give us? We wanted mod Sn minus summation over k Fk. Right? This is what we wanted. But Sn is actually just Fkn summation over k and minus sum over k Fk. Okay? Fine. Now, this is certainly going to be less than or equal to, summation k equals 0 to n epsilon mod Fkn minus Fk, okay, plus summation n epsilon plus 1 to infinity mod Fkn minus Fk. Okay, k equals n epsilon plus 1. Okay. Now, how does this help? Well, if n is greater than capital N, then something interesting happens. How was capital N chosen? It was the maximum of n1 epsilon, n2 epsilon, n epsilon of epsilon. Okay. If n is greater than capital N, then what we have is Fk of n minus Fk must be less than epsilon by 3 n epsilon. Right? So what we get is this first quantity this first quantity will certainly be less than or equal to n epsilon times epsilon by 3n epsilon, right? Why is this the case? Well, because each term mod fkn minus fk will indeed be less than epsilon by 3n epsilon, and there are n epsilon such terms, so this will be less than or equal to n epsilon times epsilon by 3n epsilon. Okay, now what about this second term where you are summing up from n epsilon plus 1 to infinity? Recall that n epsilon was chosen to make the tail of the series summation mk really small, right? We had chosen it to make the the series really small, the tail of that series. And here if you observe, you have fkn minus fk. And we know that the absolute values of mod fkn is less than mk, and the absolute value of fk is less than or equal to mk. So we can write this term as summation less than or equal to summation k equal to n epsilon plus 1 to infinity twice mk. Twice mk. This is just easy estimate. This just follows from the fact that mod a minus b is less than or equal to mod a plus mod b. But this is less than twice epsilon by 3. Okay, putting all this together, we get that mod Sn minus summation over k fk is less than or equal to less than epsilon whenever n is greater than capital N. Hence proved. So the proof is not difficult, it just involves a bit of jugglery because we are given a lot of data. Okay, so now exercise show 1 by 1 plus n power n converges to E. This is actually most of the work has been done, and you just have to apply Tannery's theorem and you will get it. I'm going to leave you with another exercise which will be expanded upon in the assignment. You are going to prove a condition, or let me just leave it as an open-ended exercise now so that you can think about it later. Think about when summation I equals 1 to infinity, summation j equals 1 to infinity, aij will be equal to summation j equals 1 to infinity, summation I equals 1 to infinity, aij. So we have this double series sort of. We are first summing up over j, then summing up over I. I'm asking when can you interchange? Think about when you will be able to interchange. Think about it using Tannery's theorem. In the exercise set, I shall give you an exercise where you give a precise condition under which this is valid, and you will prove it using Tannery's theorem. This is a course on real analysis, and you have just watched the module on the number E.